our very own Andrew Jordan, the current co-director of the Institute for Quantum Studies himself. He is a fairly recent addition to Chapman, over a year now. I think you're local here. Andrew has an illustrious career through many places. It would take far too long for him to recount. So I'll let Andrew start.
Okay, thank you, Justin, for the kind introduction. Thank you for coming on such a hot day. I'm happy to kick off our seminar series. Last year, we had a very active and I think very interesting series of speakers, and I'm hoping we can reproduce that. So I wanted to kick us off this year by giving our opening seminar. And the topic I've chosen to speak to you about today is some new work that I've done, and the paper, as you've seen in front of you, if you haven't a copy, I'll give you one. Here's one for you guys to share. Is basically done. So I wanted to present this work and get your feedback on it before I put it to the archive. So this is work done with Daniele Strupa, with Akira Harmonic, and Fabrizio and other colleagues. It came out of some discussions we were having about the notion of trying to generalize a superoscillation. So for those that don't know what a superoscillation is, I'm going to take just a few minutes and explain it to you. So the idea of a superoscillation is I have some mathematical function. And ordinarily what I can do is I have, if I suppose I define that function on some domain, 0 to L, for example, I can write this function as a Fourier series like this, where typically we would quantize Kn, or I shouldn't say quantize, this is just classical Fourier physics, as some 2 pi integer over the length of the interval we're talking about. And so this is a well-known Fourier series. I can take real and imaginary parts and construct whatever function I want. And the idea of the superoscillation, good morning, thank you. The idea of the superoscillation is that we have what's called a band-limited function. So if I look at the Fourier coefficients here, I'm going to bound either the frequency or the wave numbers between some value k min and k max, such that I have a bounded Fourier spectrum. Now, the idea behind the superoscillation is that even though, so naively you would say, what's the fastest wavelength that this function can oscillate at? Naively, you would say that there's a minimum wavelength this guy could possibly have, which is essentially 1 over the maximum value of the k value of my band. So that's as fast as the function can possibly wiggle. And the insight of superoscillations, and this was discovered by Akira Harmonic and colleagues and Michael Berry independently. There were some earlier works in radar theory, and the idea is that then I can have a function that locally oscillates faster than this function k min. So if k min is something like this, so if I plot some function, some region of the function, some small region, right, this small, something like that. So this is the behavior where this is the minimum wavelength, then I can have functions that actually oscillate locally faster than that wavelength. Okay, and this phenomenon is called superoscillation, where you can oscillate faster than this function. And there are various examples you can give. The oldest example I can give to you very simply is we'll take a particular value of this function. And that's if I have the following thing. Let's take cosine x plus IA sine x to the nth power. Okay, so here x is my variable, a and n are real parameters, and the idea is that if I expand this out into its Fourier modes, I have some maximum wavelength and some minimum wavelength, which would be set by n. Okay, so k max here would be n, the capital N, if I expand this in terms of its Fourier series. But if I look locally around x equals 0, so if I expand this around x equals 0, I have something like 1 plus IAX plus dot 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 raised to the nth power. And then if I simply re-express that because x is small as an exponential, I have e to the I a x n. Okay, and so this is around for x small. And the thing I want to bring your attention to is the fact that there is this factor a there sitting there. And so because a can be bigger than 1, this tells you that around x equal 1, this function oscillates faster with the local wave number faster than n. Okay, and so because a is equal to bigger than 1, so really the super oscillation wavelength is actually 1 over a n and not 1 over n. So this is the super oscillation effect. Okay. Now, people have been interested in this for a variety of reasons. One reason I have a project going on now with a colleague in Rochester trying to use this feature to do optical super resolution imaging. So the idea is that I would be able to use, for example, only red light, but by being able to create super oscillatory structures using the red light, I could image the image, I could get a resolution of the image as if I were using blue light, much smaller wavelength. Okay? And so this is one application this function has, and there are various other ones that we're exploring as well. But the reason I want to talk to you today is I want to spin this, I want to review this, because right now I've told you some curious fact about Fourier analysis, but originally this came out of Aronov's thinking about quantum mechanics and quantum measurement theory. And so I want to try to go back to the origins and then use that to expand out this notion of super oscillation to an arbitrary kind of so what I can do to begin to do that is I can notice, let me define a notion of the local wave number. So this would be the local rate of oscillation of a function at a particular position. Right? So what I can do is I can take this function f of x, and I can imagine expanding it in some region as e to the I k of x times x, something like that. And if I want to, I can also add some plus kappa of x times x is kind of the picture you should have in your mind. And so what I can do is I can define then these local wave numbers. So if I take the logarithmic derivative, that would be something like e to the I k of x. If I take the imaginary part of that, I'm going to define this to be some function, which I'll call k of x, in analogy to this thing here. Okay? So this is what I'm going to define as the local wave number. And then I can also define something like local growth rate if I take kappa of x, and that would be the real part of this quantity. So to go further, what I want to do is I want to then imagine, when I adopt a particular context, which is quantum mechanics. Let's imagine we go away from just any kind of function or wave-like function, thinking about these as quantum f as some kind of quantum wave function. Then what I can do is I can rewrite this expression in a clever way. So this is where we can fall a little bit into the equation. So I can write in the quantum mechanical context, this local wave number, I can write it as the real part of this quantity. Here I've replaced f by psi to tell you that this is a wave function. Like so. All right. So what is this? So let me first of all show you that that's really the same thing. What is this p operator? The p operator is the momentum in quantum mechanics, which in position space I can write as IH bar times the position derivative. Okay. So this would be this operator. And if I operate this function a p on psi, which is some wave function, this is IH bar. We'll write this as, okay, well, if I have a position operator like this, I can write this as psi prime of x, and the denominator is just the wave function or the state in the position space. I can write it like that, and of course this psi prime over psi is nothing more than the logarithmic derivative, so I can write this as ddx log psi x. Okay, and so if I take the imaginary part number into account here, then I can write this as the real part of this quantity, which is the same thing as the local wave number. All right. So why did I do this? I did this because if you follow this quantum mechanical stuff about weak measurements, you can recognize this quantity here as a weak value. Right? It's a real part of a weak value. That would be the local wave number. If I took the imaginary part of the weak value, that would be the local rate of growth. And what is this a weak value of? So more generally, we have Lev on the call who knows all about this because he helped invent it. If I have some two states, some operators A, psi like this, we define this quantity as a weak value of the operator A with a pre-selected state psi and a post-selected state phi. Okay, so this is sometimes called the weak value of A. If I want, I can decorate it with psi and phi to decide to know what the pre and post selection is. So with that in mind, and there are various properties I don't want to go into right now about this weak value, but maybe the most interesting property is that if the overlap between the initial and the final state is very small, generalized A spoils that overlap, and so this weak value can be much larger than the eigenvalues of the operator in question. Okay, so what we see here is that this is a weak value of a momentum operator with some initial state psi and some post-selected position x. All right, so the x is the post-selected position. So we can think about this as like a local weak value where the final post-selection is on a position, and the operator in question is simply the momentum. But the state is not something arbitrary. What I want to consider states which have this feature I mentioned before where there's a band limit. So if I think about expanding this function psi in the eigenbasis of momentum, so what I want is I want psi of x is going to be some sum over coefficients, Cn e to the I in x, let's say. We'll write it as some k sub n x, okay? Where the idea now is that if I think about h bar k of n, I want to bound that between some maximum, so p max, and some p min. Okay, so this is the analog of a bounded a band limit in a wave function. So you can see already something interesting happens, that if you think about this weak value then, with this kind of pre-selected state, in this post-selected state, with this momentum, the important feature is that the number here, k of x, can be bigger than the local, can be bigger than this highest value of the momentum, right? So it can exceed this p max, and that's just like what we saw over here. So we see that here locally, this function oscillates faster than n at this particular position. It goes to like an. So the same thing is happening here. I can have this value can exceed the local maximum. So that gives us a definition, right? So we're then define, if I can find my eraser. So definition. So superoscillation exists if this weak value, h bar k of x, is bigger than, say, p max for some x. All right, so that would be the region of superoscillation happening. Okay, and what you can see there is it has a very natural interpretation as the weak value exceeding the upper bound of the momentum modes of the superposition state that you started with. Now, once you see this, once you understand this point of view, it then becomes clear how I can then generalize the notion of superoscillation to any kind of observer. So here's how I'm going to define it. What I'm going to do is I'm going to restrict my attention to only post-selections on the position. So I can call these local weak values or local observables because I'm interested in always selecting on a position. I don't have to do that, but I think that's the most natural interpretation generalizing the superoscillation. So here's the generalization. Hello, Matt. So the generalization is I consider any operator O. Well, we'll make it Hermitian to be self-adjoint, to be simple. And it has some spectral analysis. Okay, so if I have some spectrum, say alpha, some lambda alpha, so that's the spectral decomposition of the operator rho, so eigenanalysis. What I want to do is I want to construct some initial function that I prepared that is a superposition. All right, so what we do is we're going to restrict these eigenvalues. Be bounded between some minimum and some maximum value. Okay, so there they are. And now I'm going to construct a state. So we define a state psi. All right, so we define this state, which is a superposition of the eigenstates of this observable O with some arbitrary complex coefficient C alpha, but such that the eigenvalues that correspond to this eigenket alpha are bounded between a maximum and a minimum value. So that's the construction of the pre-selected state. Justin.
Yeah, quick question. Are the eigenvalues of O bounded a priori, or is it only in this superposition of psi that you're bounding them?
Only in the superposition of psi. So it could be an unbounded operator in principle, but I'm choosing to only sum over some bounded set of them. Okay. Yeah, so maybe that's what's different than typically the weak value, like with spins. With spins, you always have a bounded spectrum, and so I'm thinking about possibly unbounded spectrum now, and I'll give examples of that here shortly. So I define this ket alpha, and then I define the weak value of this operator. So we'll write this as OS, not for weak, but for super, as a function of the position x, which will be x O psi over x psi. So that's the natural generalization then of this weak value that I looked at for the super oscillation, and now any observable. So I can think about whatever observable I want. I construct this state that has a bounded superposition, and then I post-select on the local position. So I'm going to define then here. So here's my new definition. I'm going to ask, when do I have a notion of super phenomena with this generalized observable? We'll use the red marker. Super phenomena happens when I take the super weak value, whenever that exceeds the maximum eigenvalue. And we can say it also, or is like, we can also say it's or less than the minimum eigenvalue. Okay, so that will occur for some value, it can occur for some particular position x, and when that occurs, that's our definition of super phenomena for arbitrary observable. Okay, questions? Yes.
You mean real part of this, or?
Yeah, so the natural thing for super oscillation would be the real part.
Complex comparison is tricky.
Yeah, so you can ask, what does the imaginary part of the super oscillation correspond to? So I showed a moment ago that corresponds to the local growth rate. So that's a phenomenon I call super growth. And so that happens when the rate of growth exceeds the band limit of the function. And you can actually use that also for super resolution imaging. I have another paper about that. So you can think about, yes, but just to maintain a strict analogy to the super oscillation, I'm going to take only the real part under consideration here. But you can also discuss the imaginary part. So good. Okay, so that's the general theory. I want to now give you some examples of that. So the first example I want to give is total angular momentum. So If I think about a particle in a box, or I talk about angular momentum on a circle, those are all mapping to the usual super oscillation case. So I want to give something that's different, and that's going to be total angular momentum. So let's go to an example. Okay. So you remember from your quantum mechanics course that if I think about total angular momentum, L squared, and I think about eigenkets, so usually if I want to diagonalize that, I can do that with two quantum numbers, the total angular quantum number and the azimuthal quantum number. And the eigenvalues of this would be h bar squared L times L plus 1, where then L is going to be 0, 1, 2, up to infinity. So this is an unbounded operator. You can have as many orbital angular momentum quantum numbers as you want. And so that's that. And if I think about what they are the eigenfunctions, if I write them in terms of theta and phi of this L and M, you maybe remember from your quantum mechanics class that these are spherical harmonics, Y, L, M, of theta and phi, like so. So what I want to do, excuse me, water here. Because I'm thinking about the position space, so the natural analog of position and the angular variables would be these theta and phi variables. So I can think about this operator expressed just like for the angular momentum was ddx. What is the angular derivative expression for the angular momentum operator? And it turns out to be this. It's an operator. So here I'm using del sub variable to indicate the partial derivative of that variable. So I have a double derivative of the polar angle. I've got a single derivative of the polar angle, and I've got a double derivative of the azimuthal angle with these coefficients that involve the polar angle as well. Okay, this is clearly quite different than the normal super oscillation case. And so once I have that operator, so then I could, for example, normally in quantum mechanics, I would give this to my students and say, can you show that this spherical harmonics obey the eigenvalue equation? Now I want to go beyond that, and I want to show something different. I want to construct this generalized weak value. One of the things you see that happens very easily if in the denominator is just the state interproduct with the local coordinate. So here it would just be the wave function of the state in the angular basis. And in the numerator, I see that I have to operate this operator onto some state alpha that involves theta and phi. Now, to satisfy my condition here, what I'm going to do is I'm only going to consider variables or eigenstates, a superposition of angular momentum L. So let's make this a little bit simpler. So we're going to construct our initial state. So some psi over Lm, CLm, YLm, theta phi. So this would be the state that I construct in general. To make things simpler, because if you look at YLm, so this involves actually some generalized Legendre polynomials and something like e to the I m theta here, I to the I m phi. This e to the I m phi is really the same thing as a super oscillation in an angular space. We already know how to do that, so let's forget about that. And so I'm going to say for simplicity, let's only sum over L and forget about the m to get some new phenomena. Good. How am I doing on time? Oh, good. Okay, so here's what we're going to do then. Let's do some. Okay, so let's write down our super angular momentum. So what is L squared super. Okay, so we can write that down. So L squared super as a function now of angle and phi. So this would be the idea. The interpretation of this would be this is a value I can assign to the total angular momentum at a particular set of angles. So it would be the following. Divided by sine theta phi. So that would be the expression for an arbitrary function. And you see what you're interested in, if you want to exceed some value, you see that kind of happens very naturally when I get a zero of the wave function, right? That's like the overlap going to zero. So that's quite a natural condition. So let's give some example here. So the example I want to give is a special case. I'm only going to superpose L equals 0 and L equal 1. Okay, so we'll say that psi is proportional to L is equal to 0, N is equal to 0, plus, and we'll put in some coefficient C here, L is equal to 1 and N is equal to 0. So that will be the superposition I consider. And so if I have N equal to 0, these spherical harmonics, L0 of theta and phi, they reduce now to the Legendre polynomials, right? So I can write them as LL of theta, Legendre polynomial. Actually, they're a function of cosine theta, I should say, like so. Okay. So in particular, for L is equal to 0, so L0 is just a constant. It's just a 1. And then L1 of cosine theta is just going to be cosine theta. Okay, and of course I could take higher order ones, but this is enough to get interesting phenomena. So if I put this expression in and put it into this expression for L theta squared, what I find is the following. So this is the result of this calculation. So put a box starting with that. So that would be the local angular momentum squared that I assign to this function as a function of theta. And you might say, well, wait a minute, Andrew. Something funny is going on here. Because if I think about plotting this as a function of theta, well, initially it's okay, because this is just 2 times c, where c is some number. But then once cosine theta passes pi over 2, it becomes negative. So I have a total angular momentum squared. It becomes negative for half of the polar angle, right? But that's okay, because this is not a real angular momentum. This is this generalized weak angular momentum. That's exactly the super phenomenon we're after anyway, where we exceed the eigenvalues. So what's the eigenvalues? So the eigenvalues are 0 and 1. So if I think about h bar squared L times L plus 1, so L equals 0, that would correspond to 0. L equal 1, that's h bar squared times 2. So my eigenvalue bound is 0 and 2. So anything outside of that bound has a super phenomenon. Okay. So I've got negative values between theta's pi to 2 pi. This is negative. So super phenomenon. Okay. If I start playing with C, I can play with C and I can actually get some divergence happening here. For example, if C goes to 1, then when this becomes negative 1, I get a divergence. If C continues to become bigger than 1, then the divergence shifts somewhere in the middle of the line. So I can all have an interesting phenomenon by playing with this coefficient C. Okay. Let me stop for a minute and ask if there are questions about that.
Yes. So originally, the way superoscillation was defined that x, p, psi. So when you generalized it, so P and X are related as like they are conjugate variables, but when you generalized it, O and X doesn't seem to have that constraint.
Yes, so I guess the commonality is that it's not that they commute to I, it's simply that they don't commute, right? So the interesting phenomenon happens when the operator in question does not commute with the final position. So if I just had a position operator, then only boring things would happen.
Okay, yes, but they don't need to be like the conjugate variables.
Not necessarily, no, this is true for any observable, right? I've completely generalized it, so any observable will work here.
Yeah, but then my next question is, given an observable and a psi, can you not choose some basis like where there will be super phenomena at some arbitrary point, like?
Yes, so if I have the state, and I have the observable, and I have the position, so this is my, yeah, so you're saying if I choose some observable, I can make it happen somewhere, right?
So I'm saying that you have O and psi fixed, but instead of X, you choose some other basis, and you can always have super phenomena at some in that coordinate space.
That's true. So if this were only a function of position, for example, then choosing this selection would not be very interesting. But if I chose, for example, momentum post-selection or energy post-selection, then something interesting could happen, right? So that's certainly true. But again, I'm trying to restrict to selecting on position because that's mostly analogous to the superoscillation. Okay, good. Maybe something I've neglected to mention I think is important is that there is a connection still with the expectation value of the observable because there is a sum rule, and I should mention the sum rule before I go on. And the sum rule is exactly analogous to what happens in the weak value physics, but it happens for the super phenomena as well, that if I take this observable OS of X, and I weight it with the wave function of X quantity squared, and integrate over X, can anyone guess what that is?
Expectation value of OS.
It's the expectation value in the state that I prepared, exactly. This is now the operator, no longer the super thing. So there's a sum rule. So if I weight these local values with the probability of being there, integrate over all this, I simply get back the expectation value of the operator. So that motivates the definition of this as the value I can assign to the observable locally at position. So that's true in general. So in particular, even though I had this weird super phenomena overall, if I weight it properly with the wave function and integrate it over everywhere, I get back to the normal conventional expectations.
Do you get anything with higher moments?
There's no sum rule in general for higher moments. Yeah. Right, because you can see that you've got just one power of psi of x here, and so if I put some kind of higher powers there, this would give something like n as this to the n. I get partial cancellation, and nothing happens in general. Okay, so now I'm going to go to the next example here, and that's the example of energy. And this is the example I'm really excited about. So let's start with the simplest possible example. Let's think about one particle in a potential well. V of x. Okay. So now my Hamiltonian, I can write down energy, particle of mass m, non-relativistic, V of x, simplest textbook example of quantum mechanics. If I have this state, the natural example, I'm going to sum over some energy eigenstates alpha, E alpha. I'm going to bound the energies between some minimum amount and some maximum. Okay? So it's an unbounded operator. I can have energies go up to infinity, but I'm going to choose to restrict to some range. what then, if I plug in this operator here and make some simplifications, what is the definition of a local energy? Well, it turns out it's a really cool formula. That's the formula. It involves, like before, two derivatives, not one. But if you just stare at that formula for a little while, what does it say? It says the energy I assign to this system at a particular position E is related to the curvature of the wave function plus the potential. But if I just stare at that for a moment, what does that remind you of? Well, it's completely general at this point. What if I just took both sides of the equation and multiplied by psi of x? It's just the Schrodinger equation, but turned upside down and written up on its head, right? So it's kind of cool. It's like the Schrodinger equation you would solve to find the eigenspectrum, but now I'm using it backwards to define the local value of the energy the particle takes at position x. Okay.
No time derivative.
No time derivative. No time derivative, exactly. We'll come back to that here in a minute. Okay, so I can construct examples in the same way I do with the oscillator out of this, but here I'm going to throw in a twist. I've got 20 minutes remaining in my talk. One of the outstanding questions that Yukiro and colleagues have been talking about is it possible not to have superoscillation just in some region of space, but to have a superoscillator everywhere in space? You say that's impossible because that would somehow break the universe, right? And in a way, it does kind of break the universe, but we'll see how in a minute. In particular, it seems to automatically contradict this kind of thumb rule. But if you take a particular kind of limit, you can show mathematically anyway that such things are possible. Okay, so here's the idea. And I call this energy out of nothing, just as a kind of tongue-in-cheek thing. What I'm going to do is I'm going to consider a sequence. And the sequence I'm going to consider is we're going to come back to our favorite problem, the harmonic oscillator. And so the potential, v of x, I'm going to index it with some number capital N. I'm going to say it's going to be 1/2 m omega n squared, x squared. So I'm going to index the frequency of this oscillator. And what I have in mind is something like this. If I plot this function, v of x versus x, so it's n equal 1, for example, would be something like this. But then n equal 2 would be something like this. N equal 3 is something like this, and so on and so forth. Now, why would I want to do such a thing? The reason is that what I want to do is I want to imagine summing, if I think about n equal 1, let's come back to n equal 1, I ask what the eigenenergies are, where there's a ladder of states that looks like this. And what I want to do is I want to imagine summing up to some maximum value of energy that can't be bigger, the system can't be bigger than that energy. So I'm going to choose that maximum value, say, to be here. So this is the ceiling, you might say, of this problem. No energy can ever be bigger than maximum energy. That's the biggest we can possibly have, right? So in particular, if I think about the energies, En, I'll index it with this big N, 1/2 h bar omega int. N plus 1/2. That would be the energies of the quantized oscillator. I arrange it so that if I put in the maximum value here, so this must be less than or equal to En max, So we'll set that to be capital N, for example. So that would be h bar omega n plus a half. And so if I choose, for example, I can have different choice of scalings for omega n, but if I choose omega n to be 1 over n, say omega 0, which will get fixed over n, then the maximum value then goes to basically 1 plus something of 1 over n, so that will then cut it off, right? So in this case, I'd only sum up to well, 1, 2, 3, 4 levels, but in this case, I'm going to come and go 6, 8, 10, and so on. You understand? So that's the construction. So it turns out, just to give you a fair warning, later on in the talk, I'll choose a different type of scaling. I'll call it omega n2, which would be omega n over n squared. And you'll see why. All right, so now, what I want to do, psi n of x, I'm going to sum over n from 1 to capital N, Cn psi n of x. What are these psi n's? These are now eigenstates of the quantum harmonic oscillator. So you remember these are something like Hermite polynomial Hn of x e to the minus 1/2 omega n x squared. I think there's a factor m over h bar, something like that. So there's a Gaussian envelope, and then there's some Hermite polynomial with a different expectation. Oh, sorry, for a different hyperparameter. So we're going to sum over these guys up to some value capital N, and then that will be our state. So the next step is a little bit of art, not just science. And the art in this talk is how do I choose these Cn to get something cool and interesting that I can deal with without resorting to a computer. So how to choose. And so that's where the black magic of the talk comes in. And I'll show you how to choose it here in just a second. All right, so here's the choice I make. Cn indexed by capital N will be the following things. So if I have some coefficients, An, to normalize these states, first of all, I'm going to throw away those coefficients, An. All right. Then I'm going to put in a binomial coefficient and choose n. So this, if you know about superoscillations, that sounds familiar. But here comes something weird. The imaginary unit raised to the nth power times another Hermite polynomial with an index that's reversed, big N minus little n, and then I put in some parameter g as its argument. Okay? So here g is a constant. Now you're saying to yourself, why on earth are you doing this crazy stuff, Andrew? What have you done? And there's a method to my madness. The method to the madness is that there is a nice identity I can use. And the identity is I want to do this sum from 1 to n. And if I choose those coefficients, it turns out that I can do this sum. Here's the identity. You may not know it, but now you do. So it's just this. You get the argument A plus IB raised to the power. Quite simple. Yeah, it's nice. So when you do that, then I can then write down the wave function psi of x. Here I called it in the paper h of x. So it turns out to be this 2g to the nth power. All raised to the nth power. Now you begin to see why there's something interesting is happening, because this g is like playing the role of little a I gave earlier in the talk. So if I expand locally here around x equals 0, I get something, okay, so I get something like, well, it's already something 1 plus linear in x. And so I would say that this is something like e to the I times this coefficient, x in over g square root omega n, times some other stuff, okay? And so in particular, you see that if I have this 1 over g here, I can make this oscillate quite quickly, getting a high energy. But in particular, now let me choose that scaling I mentioned before, omega 1. And if I choose that scaling, omega 0 over n, I can replace this by omega 0. The n appears here, and now the n cancels out.
Root, so.
Yeah, sorry, exactly. So if I have omega, so I get a square root of n, and then I get an n, right? Exactly. So it's actually even growing, still growing as n increases. Now you can see why I can also choose omega 2, right? If I choose omega 2, then it cancels exactly. The second choice. So it goes like e to the I x square root n over g. With this is omega 1 choice of n, and it goes like e to the I x over g with this omega 2 choice. Okay?
Which is then n independent.
Yes. So here's the cool thing. With this first choice, I've only taken energies up to some maximum value of energy. What was that energy again? That would be omega 0 over n times n plus a half. So for n is large, this goes to omega 0. So this is the maximum value of the energy you can possibly take. Omega is h bar omega n. You don't have to do any calculation to see immediately over here. This is a plane wave with a wave number that grows like square root of n. So the energy here locally is actually proportional to n. So this is better than superoscillations. This is not only getting a little bit better, this is getting energy that's divergent as n goes to infinity. Okay? So if this is my maximum, the more numbers I take, the actual value of the energy locally is divergent. Okay. All right, so now I get into the portion of the paper in the last 10 minutes or so, which I call quantum mimicry, which is how the function involving only low energy solutions can mimic a function with high energy solutions. High energy. I'm going to keep that picture. So let's take that second scaling now. Yeah, so I take the second scaling, I see actually, let's write it out explicitly. So psi n of x, 2g to the n, exponential minus m omega n. So now it's going to be omega 0 n squared x squared. And then I have this 1 I over g square root m omega 0 h bar x over n raised to the n. So here's the mathematical limit I want to take. I want to say, can I extend the superphenomenon to everywhere in the real line? The argument is, choose an x, you give me an x, whatever you want, it can be a million light years away, and but keep it fixed. Keep that x fixed, and now I come and take a limit where n goes to infinity. So I can forget about the normalization here, because it's an unnormalized state. I take the limit where n goes to infinity, and now you see that this actually converges uniformly to e to the I m 0 over h bar x over g. Okay, so it has an n goes to infinity limit no matter how big x is.
The exponential damping goes away.
The exponential damping goes away. That's right. So I get a plane wave essentially that exists everywhere, and if you want to put it in technically, there's the coefficient out in front that normalizes it with this prefix. So now this kind of makes your head explode because you can say, I've got this high energy solution that exists everywhere. How is it possible to reconcile with conservation energy? And I have a couple of answers to that. The first answer is just this quantum mimicry point of view. What I can think about is I can think about finding the expectation value of energy from 2 points of view. The first point of view is I can do something like this. Cn of n squared n plus a half omega h bar n divided by Cn squared n. So this is the expression, a spectral expansion for the expectation value of energy given those coefficients. Is the expected value, expectation value. So you can see immediately that if I take this to infinity, this has to involve all of these spectral weights, right? This has to involve n goes to infinity, or sorry, n goes up to n. These guys bounded explicitly. You see explicitly the omega n goes like 1 over omega n squared, for example. The biggest I can have here is n. So there's can't possibly be bigger than the largest value of omega n, obviously. Right? These have to always be less than or equal to 1. I'm normalizing properly. So this obviously must be less than or equal to omega max, right? And even actually for us, this is like omega 0 n over n squared. So this actually goes to 0 as n goes to infinity. So at the asymptotic limit, I'm using only the 0 energy states. No energy. How is it possible I get a finite energy solution? So this is like Yakir Aronov's gamma ray paradox. It calls it red to gamma. I call this 0 to hero because it's even better, right? So that's one way of thinking about it. How do you do it from another point of view? So another point of view is that I can look at the local expectation value. I'm going to calculate the same quantity, so find the same thing. So the expectation value of energy, but from a different point of view, which is this. So we'll call this mimicry. So I'm going to call it mimicry, like a imitation. I'm going to write it as an integral over space, psi n of x star. Well, the star doesn't matter because I've got this. Let's write it as an operator. Psi n of x. So that would be the local expectation value of energy divided by the same thing, but without the h. Yes, design.
So when you take this limit n tends to infinity, you don't have bound states, right? So because it becomes like the Hamiltonian becomes p squared by 2n.
That's right. In that limit, you take the limit in a funny way. So the potential actually goes to 0 in that limit. That's right. But it's very weakly bounded. If you go out to infinity, it's very weakly bounded. All right. So here's what I'm doing. I'm looking at the same quantity, energy from this point of view. I'm taking the expectation value of energy with the states locally, integrating it from some region to some region, and dividing it by this. If I do that, what I can do is I can choose Ln such that I'm only in the superoscillation region. So the condition is that Ln actually goes like square root of n for this to be true. So if I take the limit this way, what do I get? I get the super energy. I get this whatever, omega naught squared, omega naught h over g, something like that. Squared. So I get the super energy there, which is not 0. But as I take n goes to infinity, what's happening is that in this limit now, if I choose the limit appropriately, if I let this L go to infinity, then it turns out I would recover this. Okay? So what's happening is I get this local super energy, but then this function starts exploding. So I want to essentially exclude those exploding regions. If I take the limit appropriately, I cut this off at L, and then take that limit goes off to infinity, then I get the super range. So what this is telling you is that the order of operations, the order of limits is coming into play here. Hiding the limits becomes very important to get this physics. So I'm out of time. I'll just mention one last thing. You can look at this in the appendix. You can say, well, Andrew, how does this thing evolve in time? Because energy is an important quantity of time. So it turns out that if you do that, you can have an expression for the time-dependent eigenfunction. But what's weird is that if I keep infinite, I can write an explicit expression for the wave function as a function of x in time, which obeys the Schrodinger equation. Everything is fine. But as I take that for t and x fixed, if I take that limit n goes to infinity, the time dependence goes away. So what's interesting is that if I take the limit where n goes to infinity, psi n of x and t, it turns out this also goes to this function e to the I omega naught x over g, x and h bar there. And so there's no time dependence. So you can say, well, does the function still obey the Schrodinger equation? If I take the time derivative, do I get the left-hand side of the Schrodinger equation? And the answer is no. So I've actually broken the Schrodinger equation with this procedure. If I take the limit n goes to infinity first, the time dependence goes away. And so this feature actually saves energy conservation, that I'm able to then say that what I'm really not, I break the connection between time and energy in this way. Okay. So that's my talk. I think I'll stop there, and if you have any questions, we can discuss.
Questions for Andrew? Is there one online? No?
So may I ask, so that's a very general question. It reminds me of Pythagorean for the Dirac equation. Is it related to this kind of phenomenon? Superoscillations.
Yes. So what found of the Dirac equation?
Consider favorable.
This is jittering motion?
Yeah, exactly. With the jittering motion, the jittering Pythagorean how it's called. And it's related to those superoscillations that you have mentioned in the beginning of your talk.
I don't know. It's a good question. I don't know the answer to that question.
Certainly, there is no cost of action there considered. It was back at the Schrodinger's times. So
I think the answer is no, because Zitterbewegung you can express in the Heisenberg picture as the evolution of the X operator. So I think it doesn't depend on any of these interference details necessarily. It's a good question. I don't think it's the same thing.
Yes. So one, I guess, interesting point that is related to that in an indirect way is the way I motivated superoscillations was just a phenomena in Fourier theory, right, with no connection to quantum mechanics, post-selection, or anything. And so one sort of question or thing I want to add to the paper to kind of finish it off is, can we make that same kind of connection? Can we take this phenomenon in quantum mechanics and import it back over maybe into the theory of these differential equations? I think the answer is yes. I think this is kind of a general phenomenon in spectral theory of ordinary differential equations, or even partial differential equations.
I have a question. Roll this G parameter. I think you mentioned it, but then it glossed over. So G has to be less than 1 for you to get something really interesting. Is that correct?
Yeah, that's right. That's right.
So when G is less than 1, your unnormalized wave function has this G to the n power.
Right.
Which would mean unnormalized, the amplitude would go to 0 on this limit. But
That's
then you're
right.
dividing by this to normalize.
To renormalize, exactly.
Is there something funny happening there that's hiding like a
Certainly.
singular limit that's related to
Certainly. Exactly. Certainly there's something funny going on there. And the reason is if I go further out, what happens is the function starts blowing up. Right? And so on the scale of the entire function, the stuff we're talking about is actually a very, very small thing that's similar to the superoscillation effect.
Okay. So you can kind of think of this as the usual superoscillation where there's a region where it's superoscillating and then huge tail
That's right.
You're just pushing the tails
You
up.
push the tails to infinity. Exactly.
Okay, interesting.
Yeah,
That
good,
makes
good,
everything
good
super
point.
oscillate. Okay, good.
So here we've been looking at everything in terms of position, but I was wondering, there's also time comes into play if you're talking about the time-dependent Schrodinger's equation. So in terms of, and you can go to the frequency space from time space. So is there any significance of saying super oscillation in terms of time?
Yes, so certainly you can talk about super oscillation of time into space, and that's quite common, right? We've been discussing this, but yeah, I guess the question is, so in quantum mechanics, time is always a parameter, right? And so the only way you can have time operators that are not singular in some sense is if you do like a dwell time operator, something like that. Time is hard to spin between 2 points. So you can certainly think about that, and that has also, it's a spectral generation operator you can talk about. So I can talk about this kind of quantity. In fact, that's relevant to these telling time experiments. So there's a bunch of work that says how long does a particle stay in a tunneling barrier? And you can only answer the question for the ones that emerge. So it's naturally post-selected kind of question. And so there's been work, from Steinberg and colleagues on that, where you have to have weak value type formalism to be able to do that. And so I think this would be, this would be a way to generalize that. You could use it. And in fact, I think actually we have a paper, I think, with Yunjin many years ago where we did something similar to that.
So, very naive question, but so the generalization you mentioned was going from superoscillation to like it's a generalized version of superoscillation, right? That's what you say in the beginning. So the superoscillation itself, was it defined only for XP? Or so what is the generalization exactly? So is it generalized P to any observable or?
Yeah, so before you generalize it, it was just a phenomenon in Fourier series. An observation that the function can locally oscillate faster in the fastest Fourier mode. Okay, so that was the effect. But yeah, but to put that in quantum mechanical context, you can see that very naturally as saying I prepare a state that's a bounded superposition of momentum eigenstates. I have a momentum operator, that's the one I consider, and I post-select on a position. I take the real part of that, and that's like the local wave number of the function.
Anything that doesn't commute with X would give potentially interesting.
Exactly.
Another question, which is that the original super oscillations were explored by Michael Berry in optics, especially around optical vortices. You can find these anomalous local momenta, which he calls local wave number in optics. Do you know if Michael Berry or other people have looked at this angular momentum case in optics as well, or is this completely new that we should?
Not that I know of. I think I mentioned this idea at a talk this a year ago, and I think Michael Berry was there. I don't think he mentioned anything explicitly about this.
Because I'm immediately wondering, and near an optical vortex where the amplitude goes to zero, there's sort of a circulation there anyway. Maybe
Right.
It's a natural candidate experimentally where you'd see at least the angular momentum doing something funny locally.
Yeah, you can see that it would likely diverge that way.
Right. You could test your theory.
Yeah.
So now that you've broken the Schrodinger equation and this data is frozen in time, what does that mean for time and energy?
Yeah, I think it means we broke the universe. That was what it means. So, I think that's essentially the only way you can resolve this this limit. The fact you take this limit, the only way you can create energy out of nothing is if you break this connection between energy and time development.
But that's only if you do the limits in the wrong order.
Exactly. Yeah, you can always take time and its position large first, and then everything is normal. Right? But even if you don't take the mathematical limit, what I find really cool is you can always mimic it in any region you want. You can mimic a large energy solution that you desire using only 0 energy states. That's really cool. Okay.